All right, we got another great example here of a problem involving both electric fields and magnetic fields. I'll let you go ahead and have a read through it, pause it if you need to. Let's go ahead and talk about it though. So essentially we have a potential difference here of 2,100 volts. And this charge, which is a proton, is going to start right here. And remember, we do know the charge and the mass of a proton. The charge is 1.6 times 10 to the negative 19th coulombs. And the mass is 1.67 times 10 to the negative 27th kilograms. And I know you're thinking, man, Mr. Bauer, you got all that memorized? No, I don't have it memorized. I just have my formula sheet here, which tells me the charge of an electron, which is the same as charge of a proton, and it also gives me the mass of a proton. So, have I memorized this? No. But am I smart? Yes, because I use my formula sheet. So here we go. We know the charge. We know the mass of that proton. We have 2,100 volts. It's going to go from the positive to the negative, so it's going to go through that whole potential difference until it gets here to the negative side. And the first question is to find the speed once it leaves there. Now, I can think of a couple of things that include speed, right? I can think of kinematics. Kinematics is great if I have acceleration and if I have a distance and time. But as I'm looking at the information here, I don't have a distance between the plates. I don't have a time between the plates. So as much as I'd like to use kinematics because I love kinematics, it's probably not going to work here. So the next option, remember when we learned about potential and electric fields and all that kind of stuff, one of the things that we learned about was electric potential energy. And so I'm thinking, I'm probably going to start with some electric potential energy here. And as I go through this potential of 2,100 volts, all that potential is going to get turned into kinetic energy for my proton. So I'm going to say I think my electric potential energy is going to be equal to my kinetic energy. Now, electric potential energy, if we look at our equation sheet here, if we look through, we can say, well, it looks like I've got electric potential energy right here, which is equal to the charge multiplied by the potential difference that charge passes through. Wow, that's convenient. That's like exactly what this problem's saying. So my U, the change in the potential energy here, is going to be equal to Q times the change in potential. The kinetic energy, of course, is just going to be 1/2 mv squared for my particle. And luckily enough, at the very beginning, I identified for a proton my charge, which is 1.6 times 10 to the negative 19th, my potential difference, which was 2,100 volts, and my kinetic energy based off of the mass, which is 1.67 times 10 to the negative 27th kilograms multiplied by the velocity squared. And now I can calculate the velocity, which is actually what it's doing. So you'll find that I actually didn't have to do a lot of electricity magnetism stuff here. This all came down from the fact that I needed to find speed. How do I find speed? Well, either kinematics or energy. Kinematics didn't work, so I got to use energy, and everything kind of fell into place from there. So let's go ahead and let's work this out. So we're going to have 1.6 times 10 to the negative 19th. We're going to multiply by 2,100. I'm going to divide by the 1/2 there. I'm going to divide again by the 1.67 times 10 to the negative 27th. A word of caution, if you use the E, then it will group this all together as one number, right? If you do not use the E, if you write times 10 to the negative 27th, then you need to put this in parentheses. You'd have to go through and actually put parentheses around it. Otherwise, what it will do is it will divide by the 1.67 and then it'll multiply by the 10 to the negative 27th. That's not what you want. You want it to divide by this whole thing. That's the nice thing about using the calculator notation of the E, which is 10 to the. That will automatically group these together. Now, when I push enter, I do get my answer of 4.023 to 4, I guess, if I keep round up the 9. Times 10 to the 11th. But remember, that is actually equal to the velocity squared here. And so to get the final answer, I am going to need to square root the final answer. And I could have done that in the previous step, but I try to avoid situations where I have too many parentheses because it's way too easy to forget or add one in. You can do these step by step as well. I could have just multiplied those two, pushed enter, divided by 1/2, pushed enter, right? You can do that as well. So I'm going to go ahead and square root the final answer, and I am going to get a velocity of 6.34. So I'm going to go 1, 2, 3, 4, 5 spaces, so times 10 to the 5th, or in other words, 634,000 meters per second. All right, so there we go. We got our velocity, which is exactly what it was asking for in part A. Now let's move on to part B. Part B is the radius of the circular path on which the proton moves in the magnetic field. All right, so we have come here. We're going out into the magnetic field here now. And so we want to figure out, we know that as it goes this direction, it's a positive charge. So I'm using my right hand, going this direction. The field is outside of the page. And so I feel a force to the right. And so it's going to move to the right, but that force isn't always to the right. That force is always going to be perpendicular to the motion, as we've talked about in previous videos. And so we're going to go in essentially circular motion. As long as we're in a field, it's going to have that constant radius. All right. And so part B, we are trying to find the radius of that curvature. All right. All right. Now I'm noticing that I apologize. I forgot to put in the problem here that the magnetic field is 0.10 Tesla. So if you're having a difficult time with that problem in advance, that would be why. But now we have the strength of the magnetic field, and so we know that it is circular motion, and so we're going to say that the force of the magnetic field is the centripetal force. The force of the magnetic field, as we know, is QV sine theta B. The centripetal force is mv squared over r, the mass times the centripetal acceleration. We should now be able to just put all our numbers in and hopefully get the correct answer. We've got the charge of 1.6 times 10 to the negative 19th. We've got the velocity, which we just found, which was 6.34 times 10 to the 5th. We've got sine of theta, which once again, it's at a right angle, so that's going to be 1. We've got the magnetic field, which I just gave you, of 0.10 Tesla. That should be equal to the mass of 1.67 times 10 to the negative 27th times the velocity squared. I guess we could have simplified this a little bit in advance. It really doesn't matter. 6.34 times 10 to the 5th squared all over the radius. And so essentially we're going to take the radius, we're going to move it over to this side. We'll take all of that stuff and we'll move it onto the bottom of the fraction. And so we're going to try to calculate that. We'll go 1.67 times 10 to the negative 27th. We're going to multiply that by, I'm going to put it in parentheses because I got a squared there. So we'll go 6.34 times 10 to the 5th squared. Then we're going to take all of that and we're going to divide it by 1.6 times 10 to the negative 19th. We'll divide that by 6.34 times 10 to the 5th. We could have canceled out one of those. It's all right. Then we're going to divide by 0.1. When we do all of that, we end up getting a radius equal to 0.066 meters. All right, I do have two significant figures here, so my final answer technically should be in two significant figures. I guess this should probably be 6.3. This is 0.66, which is about 6.6 centimeters. Again, this is something that we could actually physically measure. All right, so there we go. We were able to work through a slightly different question using magnetic fields, using electric fields, and being able to kind of put that all together, this time with energy. All right, I hope that was helpful, and we'll see you next time.